Hello and welcome to Midnight Space. Before we journey into the quiet drama of the cosmos, take a moment to like this video and subscribe to our channel so you can drift among the stars with us, again and again. Out of curiosity, where are you watching or listening from tonight? Are you under the glow of city lights nestled in a quiet countryside, or perhaps tucked into a cozy corner of your own room? Wherever you are, know that somewhere in the vast universe, a star far more massive than our Sun is quietly living out its final awe-inspiring chapters. Tonight, we'll follow these cosmic giants on a journey few ever witness. We'll trace their life from the gentle accumulation of gas in dense molecular clouds to the searing fusion in their blazing cores, through layers of helium, carbon, oxygen, and heavier elements. Step by step, we'll see how gravity slowly tightens its grip, how the balance of radiation and pressure teeters on the edge, and how these stars eventually face their ultimate fate, a spectacular collapse that can leave behind neutron stars, magnetars, or black holes. So settle in, let your mind float with the cosmic currents, and prepare to witness the slow, inevitable death of some of the universe's most majestic inhabitants. In exploring their quiet brilliance and dramatic endings, we may also glimpse the very forces that shape the elements in our own world, and the story of existence itself. In the vast darkness between the stars, immense clouds of gas and dust drift silently, almost as if the universe is holding its breath. These are the molecular clouds, regions so cold that temperatures barely rise above 10 degrees above absolute zero, and yet so dense that gravity quietly gathers material together over millions of years. Within these clouds, pockets of turbulence swirl, twisting and stretching the gas into intricate filaments, while magnetic fields thread through the darkness, unseen but influential, guiding flows and resisting collapse. The combination of turbulence, magnetism and gravity creates a complex interplay, a cosmic choreography that determines where stars will form and how massive they might become. At the heart of this process lies a subtle mechanism known as ambipolar diffusion. It allows neutral gas particles to drift past magnetic field lines over long timescales, slowly enabling regions of higher density to coalesce despite the resistance of magnetic forces. Researchers such as Kengo Tomida have modelled this phenomenon, showing how ambipolar diffusion allows the densest cores of molecular clouds to gradually collapse under gravity, eventually reaching the critical point where nuclear fusion can ignite. It is a delicate balance. Too much magnetic resistance and the cloud will never condense. Too little, and the collapse can become chaotic, forming stars in a disordered burst rather than a regulated cluster. Some of the most remarkable insights into the earliest generations of massive stars come from simulations of population 3 stars, the first stars to form in the universe. Naoki Yoshida and his team have illustrated that these primordial giants likely exceeded 100 times the mass of our Sun, forming in isolation because the gas contained almost no metals to facilitate cooling. Without these heavier elements, the gas remained hot, resisting fragmentation, allowing only a few truly massive stars to emerge in each region. These ancient titans burned extraordinarily hot and fast, living brief, brilliant lives that enriched the surrounding space with the first heavy elements, laying the groundwork for all subsequent stellar generations. The initial conditions of a molecular cloud, however, do not determine only mass. They influence rotation, the likelihood of forming binary systems, and the ultimate angular momentum of each star. Slight differences in density or temperature can lead to dramatically different outcomes. Two regions with similar amounts of gas may produce stars of entirely different sizes simply because one experienced a subtle swirl of turbulence, or one section of the cloud collapsed slightly faster, concentrating angular momentum in a spinning core. The intricate physics of these early stages sets the stage for whether a massive star will evolve quietly, shed mass through powerful winds, or erupt in spectacular outbursts during its final phases. Clusters of stars frequently emerge from these clouds rather than solitary stars. Gravity, turbulence, and local interactions cause hundreds or even thousands of stars to form in relative proximity, shaping the dynamics of their early lives. Close encounters with sibling stars can alter rotation rates or even strip mass from one another. In some cases, massive stars are ejected from their birth clusters entirely, racing across the galaxy at hundreds of kilometers per second as runaway stars. This communal aspect of star formation has profound implications for later evolution, because a star's environment, its neighbourhood of siblings, the density of surrounding gas, and the presence of magnetic fields, continues to influence fusion processes, mass loss, and eventual collapse. Even within a single cloud, the influence of magnetism is subtle but far-reaching. Fields strong enough to affect ionized gas act almost like scaffolding, resisting collapse in some regions while permitting it in others. The neutral gas, slowly slipping past these lines, accumulates in cores that grow denser with every passing million years. Turbulence creates shocks and eddies, carving intricate patterns into the cloud. These patterns are not merely aesthetic. They determine the spacing and mass distribution of newborn stars, the seeds of cosmic diversity that will later shape galaxies. Observatories such as the Atacama Large Millimeter Array in Chile have imaged these filamentary structures in exquisite detail, revealing how the interplay of turbulence and magnetism sculpts the nursery of stars. The temperature and density thresholds necessary for the ignition of fusion are extreme. In the densest cores, gas is compressed until hydrogen atoms collide with sufficient energy to overcome their natural repulsion. Only at this point does the star ignite, marking the transformation from a mere clump of gas into a radiant furnace. For population 3 stars, the lack of metals meant that these conditions occurred at higher temperatures, resulting in cores hotter than those of stars forming today. Their rapid fusion rates made their lifespans brief in cosmic terms, often only a few million years, but their contributions to the chemical enrichment of the universe were profound, seeding the cosmos with the first carbon, oxygen, and other heavier elements. Rotation adds another layer of complexity. As a core contracts, conservation of angular momentum causes it to spin faster, much like a figure skater pulling in their arms. This rotation influences the internal mixing of material, altering fusion rates, and the distribution of heavier elements in the early life of the star. When stars form in clusters, gravitational interactions with neighbouring stars can either spin up or slow down rotation, further diversifying the outcomes. Some massive stars emerge as fast rotators, destined to experience significant mass loss, while others spin more sedately, retaining their envelopes for longer periods and altering the nature of their eventual deaths. Clusters also serve as laboratories for understanding the statistical properties of star formation. Observations of the Orion Nebula and the Tarantula Nebula reveal that even slight variations in initial conditions can produce stars of vastly different masses, luminosities, and evolutionary paths. The density of gas, the presence of magnetic fields, and the distribution of turbulence all interact to determine not only the number of massive stars formed, but also their internal structures and eventual fates. These early interactions, often invisible to the naked eye, carry forward into the later life of each star, influencing the timing of supernova, the formation of neutron stars or black holes, and the enrichment of the surrounding galactic environment. In tracing the birthplaces of these cosmic giants, we see that massive star formation is far from random. It is a process governed by a web of interdependent forces: gravity, magnetism, turbulence, and angular momentum, each playing a role in shaping the next generation of stars. From the cold, dark filaments of molecular clouds to the first ignition of hydrogen fusion, the universe has orchestrated a subtle, intricate dance that sets the stage for the life stories of the most luminous and influential stars. Every massive star carries within it the fingerprints of its birthplace, a silent testimony to the conditions that nurtured it, and a foreshadowing of the brilliant yet fleeting existence that awaits. Mass is the invisible hand that writes the story of a star's life. From the very first spark of hydrogen fusion in a nascent core, the amount of material gathered in that core dictates how quickly energy is produced, how brightly the star will shine, and how long it will endure. A star with just a few times the mass of our Sun will burn steadily, producing light and heat at a moderate pace for billions of years, while a star 10, 50, or even 100 times as massive will race through its nuclear fuel, shining with an intensity that can outstrip the Sun by hundreds of thousands of times, yet living for only a few million years in cosmic terms. Mass is destiny, quite literally, because it sets the temperature, pressure, and density in the stellar core, governing which fusion pathways are possible and how efficiently they operate. Heavier stars rely on the carbon-nitrogen-oxygen cycle as the primary mechanism to convert hydrogen into helium, a process far more temperature sensitive than the simpler proton-proton chain found in smaller stars. In cores exceeding several million degrees, this cycle dominates energy production, and the output scales steeply with temperature, causing the most massive stars to burn hotter, brighter, and faster than their less massive cousins. Even slight differences in mass can lead to dramatic divergence in evolutionary paths, with stars only a few solar masses apart experiencing profoundly different internal dynamics, wind strengths, and eventual end states. But mass alone does not operate in isolation. The chemical composition of a star, its metallicity, the proportion of elements heavier than hydrogen and helium, affects how energy is transported outward and how much mass is lost over time. Stars with higher metallicity tend to drive stronger stellar winds, losing material more rapidly and shaping both their surfaces and their cores. Hiraku Nakano, Hi, Ra, Ku Ena, K, No U, and colleagues have shown that these metallicity-dependent winds can strip away significant portions of a star's envelope, altering its luminosity, its radius, and even the timing of later fusion stages. A massive star with low metallicity may retain much of its mass, pushing it closer to the thresholds for extreme core collapse, while a high metallicity counterpart may shed enough material to live slightly longer, but ultimately still meet an explosive or dramatic fate. Binary systems add yet another layer of complexity. When two massive stars orbit closely, tidal interactions and mass transfer can spin them up or strip material from one another. Selma de Mink has illustrated how angular momentum exchange in binaries can profoundly influence rotational velocity, internal mixing, and even the structure of stellar envelopes. These interactions may rejuvenate a star by supplying fresh hydrogen to its core, or destabilize it by disturbing the delicate balance of pressure and gravity. In some cases, binary dynamics can cause stars to merge entirely, producing an exceptionally massive object whose eventual collapse might be even more catastrophic than either progenitor would have achieved alone. Not all massive stars end with a spectacular supernova. Some fail to ignite the outward shock that would expel their outer layers, collapsing directly into black holes. These failed supernovae, though largely invisible in the electromagnetic spectrum, are thought to occur when the core's mass and density exceed the thresholds that neutrino heating and shock revival can overcome. Observations of disappearing massive stars in nearby galaxies suggest that such quiet deaths may be more common than previously appreciated, hinting that the universe hosts a range of stellar endings from brilliant fireworks to silent vanishing acts. The ultimate fate of a star is thus a delicate interplay between mass, rotation, composition, and the timing of core collapse. Mass also determines the type of supernova that may occur. Stars with moderately massive cores often explode as Type II supernovae, leaving behind neutron stars with extraordinary densities, crusts only a few kilometers thick, and magnetic fields billions or trillions of times stronger than Earth's. In the case of the most massive stars exceeding several tens of solar masses, pair instability supernovae may completely unbind the star, dispersing all of its material into space without leaving a remnant. These explosions release vast quantities of energy, synthesizing heavy elements such as silicon, sulfur, and iron, enriching the surrounding interstellar medium and setting the stage for the next generation of stars and planets. Even beyond the individual star, mass shapes galactic evolution. Massive stars inject energy, momentum, and heavy elements into their environment, driving turbulence, triggering star formation, and influencing the chemical and structural development of entire stellar neighborhoods. Their winds carve cavities in molecular clouds, their radiation pressures sculpt surrounding gas, and their deaths seed galaxies with the building blocks necessary for planets and life. The influence of mass, therefore, extends far beyond the star itself, bridging the microscopic interactions in the core with the grand architecture of galaxies spanning hundreds of thousands of light-years. The speed and intensity of a star's fusion-driven life are also dictated by mass through core temperature and pressure. Stars with higher mass achieve pressures sufficient to ignite successive fusion stages beyond hydrogen burning, including helium, carbon, oxygen, and eventually silicon in the most extreme cases. Each stage occurs more rapidly than the last, a cascade of nuclear processes accelerating toward the inevitable endpoint. For a star 50 times the mass of the Sun, silicon burning may last only a few days before the core collapses, while hydrogen burning in a solar mass star continues steadily for 10 billion years. The scale and speed of these reactions illustrate the immense power hidden within the cores of massive stars and the central role mass plays in orchestrating the life story. In considering mass, we also account for its influence on rotation and convection within the core. More massive stars tend to rotate faster, which drives internal mixing, redistributes angular momentum, and can alter the distribution of chemical elements. Rotational mixing allows fresh hydrogen to reach the core, potentially extending the star's life slightly, while simultaneously transporting fusion products outward. This interplay of mass, rotation, and mixing contributes to the diversity of massive star evolution, producing a spectrum of luminosities, surface temperatures, and eventual remnant types. Ultimately, mass is the principal architect of a star's destiny, determining the energy it emits, the elements it creates, the manner of its death, and the legacy it leaves behind. Whether a star shines steadily for billions of years, or blazes fiercely for only a few million, whether it ends in a brilliant supernova or a quiet collapse into a black hole, every aspect of its existence is traced back to the weight of its original material. From the heart of the core to the outermost layers, from the birth in cold molecular clouds to the explosive or silent finale, mass guides the evolution of stars with unerring influence, shaping the universe in ways both visible and subtle. Deep within the heart of a massive star, the simple fusion of hydrogen into helium is only the beginning of a far more intricate symphony of nuclear reactions. While stars of modest mass rely primarily on the proton-proton chain to power their slow and steady glow, the most massive stars burning hotter and denser turn to the carbon-nitrogen-oxygen cycle, or C&O cycle, as the dominant mechanism for converting hydrogen into helium. This cycle depends on the presence of heavier elements, carbon, nitrogen, and oxygen, which act as catalysts, accelerating the fusion process and allowing the star to radiate immense energy. In the cores of stars tens of times more massive than the Sun, temperatures soar into the tens of millions of degrees, making the C&O cycle orders of magnitude faster than the proton-proton chain, a process that governs both luminosity and stellar lifetime. Beyond the familiar C&O cycle, other secondary fusion pathways quietly contribute to the alchemy within massive stars. The neon-sodium, or NENA cycle, involves the transformation of neon isotopes into sodium through a series of proton captures and beta decays, while the magnesium-aluminium, or MgAl cycle, converts magnesium isotopes into aluminium, also through carefully sequenced nuclear reactions. These secondary cycles may seem minor, but they can subtly influence the overall energy output, internal pressure, and even the relative abundances of elements later expelled in supernovae. Their operation is sensitive to both temperature and the specific isotopic composition of the core, meaning that tiny differences in initial stellar metallicity can cascade into noticeable variations in the star's evolution and elemental yield. The interiors of massive stars are not static either. As the core fuses hydrogen and heavier elements, rotational dynamics stir the plasma, mixing freshly synthesized material outward and bringing unburned hydrogen inward. Magnetic fields thread through this rotating plasma, transporting angular momentum and influencing the distribution of energy. Noha Sliza Mod Yusuf, Noah Li Zay Mod Sefer, has explored how rotationally induced mixing and magnetic transport interact in massive stars, demonstrating that these processes can prolong fusion stages or alter the timing of shell burning. In some cases, regions of the core experience enhanced mixing that allows fusion to proceed more efficiently, while in other zones, inhibited mixing creates pockets where nuclear reactions lag behind, producing subtle chemical inhomogeneities. Fusion in massive stars is not always smooth. Bottlenecks can form when certain reactions proceed more slowly than others, creating temporary lulls in energy production that affect temperature gradients and pressure support. These bottlenecks are particularly significant during the later stages of fusion, when the star attempts to fuse carbon into heavier elements like oxygen and neon. If a particular reaction in the chain is slower than expected, the core can accumulate material, increasing density and temperature until the reaction finally proceeds. This delicate balance highlights how microscopic nuclear physics, individual reaction rates and cross-sections, exerts control over the macroscopic structure of the star, dictating the pace of shell burning, core contraction, and eventual instability. Catalyst abundance plays a critical role as well. Stars with higher concentrations of carbon, nitrogen, and oxygen operate the CNO cycle more efficiently, generating energy at a faster rate and maintaining higher luminosities. Conversely, a slight depletion in these elements slows the cycle, extending the time spent in hydrogen burning and affecting the pressure balance that supports the star's massive envelope. These variations, though small in absolute terms, have far-reaching consequences. They can determine the timing of subsequent helium, carbon, and oxygen burning phases, influence the strength of stellar winds, and even shape the ultimate type of supernova the star will produce. The interplay between catalysts, temperature, and density is a finely tuned orchestra, ensuring that the star's energy output matches the complex demands of hydrostatic equilibrium. The microscopic events in the core manifest outwardly as observable phenomena. Variations in core energy production influence the star's surface temperature, luminosity, and radius, subtly altering its spectral classification and color. Observations of massive stars in clusters across the Milky Way show that stars of similar mass can display a range of surface properties, reflecting differences in internal mixing, reaction rates, and isotopic compositions. High-resolution spectroscopy, coupled with theoretical modeling, allows astrophysicists to infer the workings of these hidden nuclear engines, connecting subtle details of nuclear physics to the light that reaches telescopes on Earth. Rotational mixing, magnetic transport, and the presence of secondary cycles all interact in complex ways. In some massive stars, mixing can carry helium and carbon outward, creating envelopes richer in heavier elements and altering opacity. This in turn affects radiative transport, stellar wind strength, and even mass loss rates, feeding back into the star's internal pressure balance. The core and envelope are therefore engaged in a dynamic conversation, each responding to changes in the other, ensuring that energy flows outward efficiently while allowing the star to maintain structural stability for millions of years. Isotopic anomalies, often subtle, provide further insight into the star's inner workings. Variations in the abundances of neon, sodium, magnesium, and aluminium can reveal the relative efficiency of the secondary fusion cycles and the degree of internal mixing. These anomalies are detectable in the outer layers through spectroscopy and, after the star's death, in supernova remnants or meteorites that incorporate the star's expelled material. In this way, microscopic processes leave macroscopic fingerprints, allowing scientists to reconstruct the fusion history of a star long after its light has faded. Even with all these mechanisms operating, the star must maintain a delicate balance between energy generation and gravitational collapse. Each nuclear reaction, each proton capture, and each decay event contributes to pressure that counteracts gravity. When the rate of energy production shifts, whether due to a bottleneck, a variation in catalyst abundance, or rotationally induced mixing, the star responds by adjusting its internal structure. Layers expand or contract, convection zones shift, and fusion proceeds in a self-regulating cycle that is remarkably robust, yet exquisitely sensitive to initial conditions. The combined effect of the CNO cycle, secondary fusion pathways, rotational mixing, and magnetic transport shapes the star's lifetime and ultimate fate. Faster fusion accelerates the star's life, producing more intense radiation and stronger winds that can strip outer layers. Slower fusion prolongs life, but still marches inexorably toward the final stages of helium and carbon burning. Observations and simulations reveal a spectrum of possibilities, demonstrating that even within the same mass range, stars may follow divergent evolutionary paths, each sculpted by the interplay of nuclear physics, rotation, and magnetism. Ultimately, the fusion engines within massive stars illustrate the profound connection between the smallest scales and the largest consequences. Microscopic nuclear reactions, catalyzed by specific elements and influenced by rotation and magnetic fields, govern the structure, luminosity, and longevity of stars. The energy produced within these hidden cores illuminates galaxies, drives winds that shape interstellar clouds, and sets the stage for the dramatic deaths that follow. In understanding these fusion engines, we glimpse the intricate choreography of forces that transforms ordinary hydrogen into the building blocks of planets, life, and everything that reaches beyond the stars. Within the simmering interiors of massive stars, energy does not flow in simple straight lines. Convection arises naturally whenever the hotter, less dense material in the core is buoyant, relative to cooler, denser layers above. This rising and sinking of plasma efficiently transports energy outward, preventing the star from overheating and maintaining the delicate balance between gravity and internal pressure. Convection is most prominent in regions where fusion proceeds rapidly, such as the shells of hydrogen and helium burning, where temperature gradients are steep and energy production is intense. These convective zones form the beating heart of the star, transporting heat and freshly synthesized elements, and setting the stage for more complex interactions in later stages. Beyond simple convection lies semiconvection, a subtler instability that occurs when layers are stable against convection, according to the standard Schwarzschild criterion, but are destabilized when composition gradients are considered. In these zones, material may slowly mix, creating a bridge between fully convective regions and stably stratified layers. This process is particularly relevant in massive stars, where shells of differing compositions, hydrogen, helium, carbon, and oxygen, stack atop one another like layers of an onion. Semi-convective mixing regulates how elements are distributed within these shells, influencing subsequent fusion rates and the star's thermal evolution. The effect is gradual but profound, allowing stars to maintain core temperatures and pressures suitable for extended fusion, while preventing premature collapse. Thermohaline mixing adds yet another layer of complexity. This phenomenon arises when a heavier layer of material overlies a lighter one due to differences in composition rather than temperature. In massive stars, this often occurs when helium-rich material sits atop hydrogen-rich regions, creating a salt finger instability that slowly drives vertical mixing. Although subtle, thermohaline processes contribute to the transport of chemical species, allowing fusion products from inner shells to migrate outward and fresh fuel to be drawn inward, subtly altering the star's luminosity and energy distribution. These slow, creeping currents might be invisible to the naked eye, but over thousands or millions of years, their cumulative effect shapes the star's internal structure and its eventual death. Late-stage shell interactions present another dimension of instability, as heavier elements ignite in concentric layers, carbon, neon, oxygen, silicon. Energy release becomes more violent and uneven, generating waves and eddies that ripple through the surrounding shells. Alexander Heger, Elix Sciam, has modelled these late-stage processes, showing that shell burning is far from uniform. Instead, it can produce fluctuations in density, temperature, and composition, creating pockets of enhanced fusion and regions where reactions lag. These variations can amplify over time, contributing to asymmetries that influence the dynamics of the eventual supernova, affecting both the distribution of ejected material and the rotational properties of the remnant core. Internal gravity waves act as silent conveyors of angular momentum, moving energy and rotational momentum between different layers of the star. Quaternary and Chiode have demonstrated that these waves, generated in convective zones, can propagate into stably stratified layers, redistributing rotation rates and altering the balance of centrifugal support in the core. The cumulative effect of these waves can spin up or slow down certain regions, subtly influencing the star's structure and the timing of core collapse. These processes illustrate how small, often invisible perturbations within the interior can exert long-term influence, guiding the star's evolution toward its final, catastrophic stages. Even minor fluctuations can have outsized consequences. Tiny density variations or local shifts in fusion rates can grow through feedback mechanisms, creating larger asymmetries across shells. Over thousands of years, these perturbations become significant enough to shape the geometry of the pre-supernova core, influencing the direction and intensity of the eventual explosion. The star, in a sense, rehearses its death over millions of years through this intricate interplay of instabilities, each one quietly amplifying the effects of the others, preparing the core for a dramatic finale. Magnetic fields add yet another layer of complexity to the dance of instabilities. When a rotating star develops strong internal magnetic fields, they can act like springboards, transferring angular momentum between the core and outer layers and influencing the speed at which different shells rotate. These magnetic springboard instabilities can alter convective flow patterns, enhance mixing in some zones, and suppress it in others, producing subtle but measurable changes in energy transport. In rapidly rotating massive stars, these fields may also help drive asymmetries that later manifest in directional ejection, during supernova explosions, shaping the distribution of matter and the spin of resulting neutron stars or black holes. The interplay of convection, semi-convection, thermohaline mixing, shell interactions, gravity waves, and magnetic forces creates a highly dynamic interior where energy is constantly redistributed and chemical species are shuffled across the star. These processes operate across vast scales, from microscopic nuclear reactions to the macroscopic motion of thousands of kilometers of plasma. The result is a stellar engine that is both remarkably stable and exquisitely sensitive, able to maintain equilibrium for millions of years while simultaneously preparing for a dramatic and complex end. Observationally, these internal processes are reflected in subtle changes in luminosity, surface temperature, and spectral features. Massive stars often exhibit pulsations, variations in brightness caused by convective and wave-driven disturbances that propagate to the surface. Detailed astroseismology allows scientists to infer the behavior of these internal instabilities, connecting surface oscillations to deep-seated processes. Through careful measurement, researchers can reconstruct the star's internal dynamics, revealing the otherwise invisible dance of convection, waves, and magnetic fields. In essence, the interiors of massive stars are never still. They are vast, multi-layered arenas of motion and mixing, where subtle instabilities orchestrate the transport of heat, elements, and momentum. Each layer influences the next, creating a chain reaction that carries the star from relatively stable hydrogen, burning toward the complex and volatile stages of silicon burning. The result is a star whose final moments are shaped by millions of years of delicate interactions, a ballet of instabilities that quietly prepares the universe for the dramatic spectacle of stellar death and leaves an enduring imprint on the composition and structure of the cosmos. Massive stars are not rigid spheres. They spin, stretch, and twist in ways that profoundly influence their evolution. Differential rotation occurs when different layers of a star rotate at different speeds, a natural consequence of conservation of angular momentum as the core contracts and the outer envelope expands. The inner core may spin many times faster than the surface, creating shear forces that stir the plasma and redistribute energy and elements. This coupling between the core and envelope is essential in regulating the internal structure, ensuring that heat, pressure, and chemical composition remain balanced even as the star evolves through its various fusion stages. Angular momentum transport is a key factor in how rotation shapes the star's destiny. Without mechanisms to redistribute angular momentum, the core could spin so rapidly that centrifugal forces would counteract gravity, disrupting fusion and destabilizing the star. Fortunately, a combination of rotationally induced mixing, meridional circulation, and turbulent diffusion work together to transfer angular momentum outward, allowing the star to maintain equilibrium while still preserving enough spin to influence later stages. These processes are subtle, operating over millions of years, yet they leave a lasting imprint on the structure and eventual fate of the star. Magnetic fields are intertwined with rotation, amplifying and regulating motion within the star. Henk Sprut proposed dynamo mechanisms whereby differential rotation can generate and sustain magnetic fields deep within the stellar interior. These fields act as channels for angular momentum transport, allowing the core and envelope to communicate more effectively and stabilizing rotational shear. Magnetic torques can slow down rapidly spinning regions, while simultaneously channeling energy in ways that influence mass loss and the distribution of fusion products. In essence, magnetism acts as both a regulator and a conveyor, shaping how the star spins and evolves over time. Rotational mixing enhanced by magnetic fields moves chemical elements throughout the stellar interior. Helium, carbon, and oxygen produced in the core are carried outward, while fresh hydrogen from outer layers can be transported inward to prolong fusion. This circulation not only affects the rate of nuclear burning, but also the temperature and density profiles of the star. Stars with stronger rotational mixing often exhibit higher luminosities and more homogeneous interiors, while slower rotators may develop more stratified structures with pronounced shell boundaries. These internal flows subtly dictate how quickly a star moves through its fusion stages and how massive its core becomes before collapse. Magnetically driven mass loss is another crucial consequence of the interplay between rotation and magnetic fields. Strong surface magnetic fields can channel stellar winds along particular directions, creating anisotropic outflows that remove angular momentum and shape the circumstellar environment. These winds are not merely cosmetic. They regulate the mass retained in the envelope, the pressure at the surface, and the overall spin of the star. Over time, the combined effect of rotational mixing and magnetically guided mass loss influences whether a star will end as a neutron star, a magnetar, or collapse directly into a black hole. Magnetorotational equilibrium describes a delicate balance in which centrifugal forces from rotation, pressure gradients from nuclear fusion, and magnetic stresses coexist to maintain structural stability. When this equilibrium is achieved, the core spins at a rate that maximizes internal mixing without destabilizing the star. If the balance is perturbed, either by excessive spin or weakening magnetic fields, localized instabilities can develop, potentially accelerating core collapse or triggering asymmetries in the outer layers. These asymmetries are critical for shaping the geometry of the eventual supernova, influencing the distribution of ejected material and the spin of the remnant. Rotation and magnetism are intimately connected to the formation of magnetars, the ultramagnetized neutron stars that possess fields trillions of times stronger than Earth's. The combination of rapid core rotation and strong internal magnetic fields can amplify magnetic intensity during collapse, producing these extraordinary objects. Similarly, the orientation and strength of magnetic fields can channel supernova explosions into non-spherical shapes, leading to bipolar outflows, jets, or clumpy ejecta. Observations of supernova remnants often reveal these patterns, providing evidence of the rotational and magnetic forces at work during the star's final moments. The transport of angular momentum is not uniform. Core envelope coupling, mediated by both magnetic and hydrodynamic processes, ensures that the star behaves as an integrated system rather than as disconnected layers. Shear-induced turbulence converts rotational energy into heat and motion, while magnetic stresses distribute momentum in complex ways. This coordination allows the star to endure high rates of energy production without tearing itself apart, preserving the structural integrity necessary to sustain fusion through multiple stages. It also ensures that the core retains sufficient angular momentum to impact the dynamics of the supernova, the formation of neutron stars, and the generation of gravitational waves. Even minor variations in initial rotation rates can lead to dramatically different outcomes. Two stars of identical mass may evolve quite differently depending on the distribution of angular momentum inherited from their molecular cloud. A faster spinning star may experience enhanced mixing, stronger mass loss, and a more homogeneous interior, while a slower rotator might retain stratified shells and follow a more conventional fusion timeline. These differences influence luminosity, surface temperature, wind strength, and ultimately the mass and composition of the core at the time of collapse. The sensitivity of massive stars to rotational properties underscores the intricate interplay between initial conditions and eventual fate. Observationally, the effects of rotation and magnetism manifest in spectral line broadening, surface chemical abundances, and variability in brightness. Stars with faster rotation exhibit broadened spectral lines due to Doppler shifts across the stellar disk, while surface enrichment in helium, nitrogen, or carbon can indicate efficient rotational mixing. Stellar magnetism, though harder to detect directly, can be inferred through polarization measurements and the structure of stellar winds. Together, these observational signatures allow astrophysicists to reconstruct the rotational and magnetic histories of massive stars, linking measurable features to the hidden internal dynamics that govern their evolution. The complex dance of rotation and magnetism extends into the late stages of stellar life. As the core contracts toward collapse, rotational and magnetic stresses increase, influencing the symmetry and energy distribution of the supernova. Regions of faster spin may launch jets or directional outflows, while magnetic fields channel energy in ways that alter the explosion's geometry. The final spin of the remnant neutron star or black hole is a legacy of these processes, reflecting the careful balance achieved over millions of years. In this way, the quiet spinning and unseen magnetic scaffolding of the star guide not only its life but also its dramatic death, leaving an imprint on both the immediate environment and the wider galaxy. Rotation and magnetism are, in essence, the invisible sculptors of massive stars. They regulate internal motion, chemical distribution, mass loss, and energy output, while determining the geometry and dynamics of stellar death. From core contraction to surface winds, from nuclear burning to magnetic torques, These intertwined forces orchestrate the star's evolution, ensuring that even within apparent calm, a hidden ballet of motion and energy shapes the destiny of some of the universe's most magnificent and influential objects. Deep within a massive star, the interior resembles a celestial onion, composed of concentric shells, each burning a different element at temperatures and densities tailored to the fusion of that particular material. The outermost layer is a shell of hydrogen, where fusion converts hydrogen into helium through the carbon-nitrogen-oxygen cycle. Beneath this lies a helium-burning shell, producing carbon and oxygen, followed by successive shells of carbon, neon, oxygen, and silicon, each igniting only when the temperature and pressure of the underlying core reach the thresholds necessary to overcome the repulsive forces between atomic nuclei. At the very center rests the iron core, a region where nuclear fusion no longer yields energy, signaling the approach of the star's final, inevitable collapse. Three-dimensional hydrodynamical simulations have revealed that these layers are far from the idealized, perfectly spherical shells often depicted in two-dimensional models. Instead, turbulence, rotation, and convective flows create ripples, eddies, and instabilities that interact across shells, producing variations in density and temperature. Alex Heger, and his collaborators have extensively modeled these interactions, showing that shell burning is a dynamic, often chaotic process, with energy and material flowing between layers rather than remaining confined. Such interactions can create pockets of enhanced fusion, regions where burning is temporarily suppressed, and channels through which elements mix, subtly altering the star's internal composition. Intershell convection, a form of mixing between adjacent burning zones, contributes to this dynamic structure. Heat and fusion products can migrate from one shell to another, influencing reaction rates, pressure distributions, and the timing of ignition in overlying layers. This process is particularly important during the late stages of stellar evolution, when the outer layers are still burning hydrogen or helium, while the inner shells ignite progressively heavier elements. Convection between shells helps maintain structural stability, transporting energy efficiently and ensuring that the star does not collapse prematurely, while also creating localized asymmetries that will later influence supernova explosions. Wave-driven mixing further complicates the interior dynamics. Convective motions in one shell generate internal gravity waves that propagate into adjacent shells, carrying energy and angular momentum with them. These waves can induce subtle motions in otherwise stable layers, redistributing elements and energy in ways that alter fusion efficiency and core growth. Over thousands of years, the cumulative effect of these waves can be significant, reshaping density gradients, affecting rotational profiles, and influencing the preparation of the core for collapse. This constant interplay between convection, wave propagation, and nuclear burning ensures that the star is never truly static, even as it appears tranquil from the outside. Observationally, the signatures of layered interiors manifest in the spectra of massive supergiant stars. Surface abundances of carbon, nitrogen, oxygen, and heavier elements can hint at the internal transport of material, revealing the mixing history and the efficiency of nuclear burning in underlying shells. Variations in luminosity, pulsations, and subtle spectral line shifts can indicate the presence of convection currents and wave interactions deep within the star. By studying these fingerprints, astronomers can infer the structure, composition, and dynamics of interiors that remain hidden from direct observation, linking theoretical models with measurable quantities. The progression from one burning shell to the next is governed by fundamental principles of nuclear physics. Each fusion reaction requires a minimum temperature and density to proceed at a meaningful rate, and the release of energy from each shell contributes to the pressure that supports the overlying layers. For example, carbon burning requires core temperatures around 600 million Kelvin, while silicon burning ignites at roughly 3 billion Kelvin. These extreme conditions create short-lived shells that evolve rapidly, lasting only days to months for the heaviest elements, while the hydrogen and helium shells endure for millions of years. The timing and overlap of these shells are crucial in determining the structure of the core and the distribution of elements shaping the star's fate. Massive stars often develop rotation profiles that vary with depth, adding further complexity to the layered interior. Differential rotation can twist and distort shells, creating shear forces that enhance mixing and energy transport. Magnetic fields, amplified by internal dynamos, interact with rotational motion to stabilize some regions while destabilizing others, producing anisotropic flows that influence shell burning and core growth. These combined effects ensure that no two massive stars are identical in their internal structure, even if their initial mass and composition are similar. The diversity of outcomes highlights the sensitivity of stellar evolution to initial conditions and internal processes. As heavier elements accumulate in the inner shells, energy production becomes increasingly unstable. Silicon burning, for instance, occurs in a series of nuclear reactions that produce iron group elements, generating heat in a short, intense burst that rapidly increases the density and temperature of the core. The energy generated in these deep layers exerts pressure on the overlying shells, driving convection and wave propagation outward. In turn, the outer shells respond dynamically, adjusting their thickness, density, and energy transport to maintain hydrostatic equilibrium. This feedback between layers is a hallmark of massive star interiors, demonstrating the delicate balance required to sustain these cosmic giants. The chemical stratification of the star also affects its ultimate fate. The size and composition of the iron core, shaped by the preceding fusion and mixing processes, determine whether the star will collapse into a neutron star, form a black hole, or undergo a pair instability supernova. The amount of material in the overlying silicon, oxygen, and carbon shells influences the energy of the explosion, the ejection of heavy elements, and the distribution of material into the surrounding interstellar medium. Each shell, each convective eddy, and each wave-driven perturbation contributes to the narrative of the star's final moments, linking the microphysics of fusion with the macroscopic spectacle of stellar death. Through the combination of nuclear burning, convection, rotational effects, wave-driven mixing, and magnetic interactions, massive stars maintain a complex but remarkably stable layered structure. This stellar onion is not static, but dynamic, continuously evolving as energy and matter circulate between shells. The interplay between these processes ensures that the star can sustain high rates of energy production, transport newly formed elements, and maintain equilibrium for millions of years, all while quietly preparing the core for its dramatic and inevitable collapse. In understanding the structure and behavior of these layered interiors, we gain insight into both the life and the eventual death of the most powerful engines in the universe. As a massive star approaches the final stages of its life, the fusion of lighter elements gives way to the burning of progressively heavier nuclei, culminating in the brief yet intense phase of silicon burning. In these final moments, temperatures soar to nearly 3 billion Kelvin, and densities climb to billions of grams per cubic centimeter. Silicon nuclei collide with such energy that they fuse into iron group elements, releasing energy in a series of rapid, high-intensity reactions. This stage is fleeting, often lasting only a few days for the most massive stars, yet it is critical as it builds the core that will eventually collapse under its own weight. During silicon burning, an important phenomenon known as alpha-rich freeze-out can occur. In this process, the intense temperature and neutron flux allow some nuclei to capture alpha particles, helium nuclei, faster than they can decay, producing a spectrum of proton-rich and neutron-rich isotopes. These exotic fusion pathways contribute to the diversity of elements in the star's interior and set the stage for the complex nucleosynthesis that will occur once the star explodes. The abundance and distribution of these isotopes influence the dynamics of the core and the efficiency with which energy is transported outward, subtly guiding the star toward its final collapse. Electron capture is another crucial process in these extreme environments. As the core becomes denser, electrons are forced into proximity with atomic nuclei, and under sufficient pressure, they can be absorbed by protons in the nucleus, converting them into neutrons and releasing neutrinos. This process gradually reduces the electron pressure that supports the core against gravity, accelerating the contraction of the core and contributing to the onset of collapse. Neutronization, the transformation of protons into neutrons, marks the transition from a stable iron core to a protoneutron star, a dense object in which nuclear and degeneracy pressures compete to halt further collapse. Neutrino-cooled cores play an essential role in regulating the energy balance during these late stages. According to studies by Cristina Volpe, Christy, Den, Ivo, LP, and others, the immense production of neutrinos carries energy away from the core efficiently, allowing the star to reach even higher densities without immediate explosion. These ghostly particles, interacting only weakly with matter, escape almost unimpeded, cooling the core and influencing the timing of collapse. The sheer number of neutrinos produced is staggering. In the final seconds before core collapse, a star may emit more neutrinos than there are photons in the entire visible universe at that moment, carrying away an enormous fraction of the star's energy. The formation of a protoneutron star is the natural consequence of this sequence of events. As electron capture continues and densities surpass roughly 100 trillion grams per cubic centimeter, the core becomes dominated by neutrons. Degeneracy pressure from neutrons halts further collapse, at least temporarily, producing a hot, dense core only a few tens of kilometers across, yet containing more mass than the Sun. The properties of this protoneutron star, its rotation rate, magnetic field, and thermal profile, are shaped by the preceding fusion and mixing processes, as well as by the interplay of neutrino emission and angular momentum transport. These conditions are also essential for the R process, or rapid neutron capture process, a primary mechanism for synthesizing heavy, neutron-rich isotopes beyond iron. In the turbulent environment of the collapsing core, free neutrons are abundant, and nuclei capture them at rates far exceeding beta decay. This rapid sequence builds rare isotopes of elements such as gold, platinum, and uranium, dispersing them into the interstellar medium once the outer layers are expelled. The interplay of silicon burning, alpha-rich freeze-out, and neutronization ensures that the ingredients for these exotic nuclei are present at precisely the right moment, setting the stage for some of the universe's most precious elements to emerge. Weak interactions, though subtle, are instrumental in determining the core composition at collapse. Electron captures, beta decays, and neutrino emissions govern the ratio of protons to neutrons, affecting not only the density and stability of the protoneutron star but also the spectrum of isotopes synthesized in the surrounding shells. Small variations in these interactions can shift the timing of core collapse, the efficiency of energy transport, and the composition of matter that will later be ejected in the supernova. These microscopic processes, operating over infinitesimal timescales, have macroscopic consequences for the star, its remnants, and the galactic environment. The delicate balance between energy production, neutrino cooling, and neutronization governs the final evolution of the star's core. As fusion-generated pressure falters and electron degeneracy diminishes, the core contracts rapidly, reaching densities where nuclear forces become dominant. This compression triggers further neutronization, accelerates neutrino emission, and drives the formation of shock waves that will eventually propagate outward. Each shell surrounding the core responds dynamically, with convective flows, wave-driven mixing, and rotational effects modifying how energy and matter are distributed. The interior of the star is a roiling dynamic arena, in which microphysical processes and macroscopic forces intersect to determine the outcome of a colossal cosmic drama. Observations of supernova remnants and isotopic anomalies in meteorites provide tangible evidence of these processes. The presence of heavy, neutron-rich isotopes, the ratios of elements in ejected material, and the energy distribution in supernova-like curves all reflect the interplay of silicon burning, alpha-rich freeze-out, electron capture, and weak interactions. By combining theoretical models, three-dimensional simulations, and observational data, astrophysicists can reconstruct the inner workings of stars at the moment of collapse, gaining insight into the fundamental nuclear physics that drives cosmic evolution. In understanding exotic fusion and neutronization, we see that the interior of a massive star is far from static. It is a dynamic environment in which temperature, density, and composition evolve rapidly, where neutrinos escape to cool the core, and where nuclei are transformed through both fusion and weak interactions. These processes are the architects of the star's final destiny, dictating the formation of neutron stars, influencing the nature of supernova explosions, and creating the heavy elements that seed future generations of stars and planets. In every sense, the core is both a crucible and a clock, marking the final chapters of a star's life while forging the building blocks of the universe. Some massive stars enter the final stages of their lives with a restlessness that belies the calm we might imagine from their distant light. Luminous blue variables, or LBVs, are among the most intriguing of these restless stars, pulsating with dramatic changes in brightness, and occasionally shedding vast amounts of material into the surrounding space. These episodic mass loss events are not merely surface-level phenomena, They reflect the deep internal instabilities that have been brewing for thousands or millions of years. The outer envelope swells and contracts, waves of energy ripple through the layers, and the star begins to reveal signs of its approaching end. Studies by Jose Gros, Hauken, have provided detailed insights into this pre-supernova variability, showing that changes in luminosity and surface temperature can act as subtle harbingers of impending collapse. Some LBVs exhibit sudden increases in brightness, ejecting material equivalent to several solar masses over relatively short timescales. These outbursts, though not explosive in the same sense as a supernova, fundamentally alter the star's environment, forming dense circumstellar shells that will later interact with the shock waves from the core collapse. Observations of stars such as Eta Carinae in our own galaxy demonstrate the scale of these events, with ejected material stretching across light years and carrying a significant fraction of the star's angular momentum. Wave-driven mass ejections contribute further to this dynamic environment. Convective motions in the deep interior generate internal gravity waves that propagate outward, imparting energy to the outer layers. When these waves reach the surface, they can accelerate material to velocities sufficient for escape, contributing to the formation of circumstellar shells. These shells, composed of hydrogen, helium, and heavier elements synthesized in prior fusion stages, encircle the star in intricate patterns. The density, velocity, and asymmetry of these shells carry fingerprints of the internal processes, providing clues about the star's core activity and the imminence of collapse. The presence of circumstellar material has direct consequences for the eventual supernova. When the core finally succumbs to gravity, the outgoing shock wave interacts with these pre-existing shells, producing enhanced brightness, irregular light curves, and a symmetric ejecta. Early ejections can therefore dictate the geometry of the explosion, channeling energy in particular directions and amplifying certain features in the supernova remnant. The interplay between wave-driven mass loss and core collapse ensures that the star's last gestures are imprinted across light years of space, a subtle foreshadowing of the explosive finale. LBVs also illustrate the intimate connection between surface variability and deep interior dynamics. Pulsations, both radial and non-radial, can transport energy from burning shells toward the surface, affecting the timing and intensity of mass ejections. Variations in core pressure, combined with rotational and magnetic effects, generate instabilities that propagate through multiple layers. This feedback loop demonstrates that the outer chaos of the envelope is a reflection of the inner order of the star, with each pulse and outburst narrating the story of what is happening deep within. The asymmetry of mass ejections plays a critical role in shaping later events. Material is rarely expelled uniformly, and irregularities in the circumstellar shells influence the directionality of shock propagation during the supernova. Dense clumps or faster-moving streams of gas can channel energy, produce jets, or amplify asymmetrical features in the remnant. Observations of supernova remnants show evidence of these early disturbances, with knots of heavy elements and unevenly distributed ejecta, pointing to pre-collapse activity that subtly orchestrated the explosion. Moreover, the timing of these pre-supernova events provides valuable insight into the stages immediately preceding core collapse. A star may experience enhanced variability months, years, or even decades before the final event, giving astronomers potential warning signs. Monitoring LBVs and other massive stars with precision photometry and spectroscopy allows scientists to link surface phenomena to the underlying physics of the collapsing core. Variations in luminosity, spectral lines, and wind properties act as diagnostic tools, revealing internal mixing, fusion rates, and even neutrino emissions indirectly. The energetic environment around LBVs is shaped not only by episodic outbursts, but also by steady winds, which carry away angular momentum and modify the star's mass profile. The combination of continuous mass loss and sudden ejections ensures that the star's envelope is constantly evolving, influencing both the pressure balance and rotational characteristics of the core. As a result, the final collapse is rarely symmetric. Instead, it is molded by millions of years of gradual and violent processes that subtly shape the progenitor star's destiny. Understanding these pre-supernova behaviors underscores the interconnectedness of stellar interiors and envelopes. The pulses, mass loss, and wave-driven ejections are not random. They are direct expressions of internal fusion, convection, and magnetic activity. Observing these phenomena in nearby massive stars allows astrophysicists to reconstruct the sequence of events leading to collapse, connecting subtle surface variability to the powerful physics of nuclear burning, neutrino emission, and angular momentum redistribution within the star. Ultimately, luminous blue variables exemplify the intricate choreography that governs a massive star's final stages. Each pulse, each ejection, and each circumstellar shell tells a story of internal tension, energy transport, and impending transformation. As these stars teeter on the brink of collapse, their outer envelopes act as both witnesses and participants, shaping the explosion to come while silently recording the history of processes that have unfolded deep within. The quiet unrest of the surface offers a window into the storm that is yet to arrive, a reminder that even before the grand finale, massive stars are dynamic, expressive, and profoundly influential in the cosmic landscape. As a massive star exhausts the fuel that has powered its brilliance for millions of years, the core faces a delicate but inexorable struggle between gravity and the quantum forces that resist compression. Electrons, which have been providing pressure to counteract gravity through the Pauli exclusion principle, are packed ever more tightly as the core contracts. This pressure, known as electron degeneracy pressure, can support a core only up to a certain mass. This threshold, known as the Chandrasekhar limit, is approximately 1.4 times the mass of the Sun. Beyond this limit, electron degeneracy alone is insufficient to halt collapse, and the core plunges toward a density where new physics takes over, initiating a dramatic and irreversible contraction. As the core compresses beyond the Chandrasekhar limit, electrons and protons are forced into close proximity, and electron capture converts protons into neutrons. The resulting neutron degeneracy pressure, arising from the Pauli exclusion principle applied to neutrons, provides a new form of support against gravity. In these extreme conditions, the density can reach hundreds of trillions of grams per cubic centimeter, creating an environment where even exotic particles such as hyperons, strange quarks, or even quark matter may form. Theoretical studies, including work by Mark Alford, suggest that the cores of the most massive stars could transition to these exotic states, fundamentally altering the stiffness of the equation of state and influencing whether the core halts as a neutron star or continues collapsing into a black hole. For stars at the uppermost end of the mass spectrum, pair instability physics introduces an entirely different pathway. In cores exceeding 100 solar masses, temperatures can become so extreme that high-energy gamma photons spontaneously create electron-positron pairs. This process reduces radiation pressure, which normally supports the star against gravity, leading to a partial collapse. The resulting contraction triggers runaway nuclear burning, particularly of oxygen, producing an explosion that can completely unbind the star, leaving no remnant behind. Pair instability supernovae are rare but spectacular, and they provide a mechanism for dispersing enormous amounts of heavy elements into the interstellar medium, enriching future generations of stars and planets. Rotation adds further complexity to the dynamics of core collapse. As the star contracts, conservation of angular momentum causes the core to spin ever faster, much like a figure skater pulling in their arms. Differential rotation between the core and outer layers generates shear forces and turbulence, redistributing angular momentum and influencing the geometry of the collapse. In some cases, rapid rotation can produce flattened or oblate cores, driving directional flows and potentially contributing to jet-like structures during the explosion. The combination of rotation and magnetic fields can amplify these effects, shaping both the dynamics of the supernova and the properties of the remnant object. Magnetic fields play a similarly critical role. Strong fields, amplified during collapse, can exert stresses that modify the distribution of angular momentum and energy. Magnetorotational instabilities may arise, converting rotational energy into magnetic energy and enhancing anisotropies in the collapsing core. These instabilities can drive polar outflows, influence the development of jets, and affect the explosion symmetry. In the most extreme cases, magnetic fields and rapid rotation can contribute to the formation of magnetars, neutron stars with surface magnetic fields trillions of times stronger than Earth's, which can release intense bursts of high-energy radiation long after the initial collapse. The composition of the core at the moment of collapse is decisive in determining the final remnant. A core dominated by neutrons may stabilize as a neutron star, supported by neutron degeneracy pressure and nuclear forces. If the core mass is higher, Exceeding roughly 2 to 3 times the mass of the Sun, even neutron degeneracy is insufficient, and the collapse continues unabated, producing a black hole. In between, rapid rotation and strong magnetic fields can produce an intermediate outcome, forming a highly magnetized neutron star with extreme rotational energy. The diversity of outcomes reflects the intricate interplay of initial mass, core composition, rotation, magnetic fields, and exotic particle physics. During the collapse, the core's density and temperature rise to staggering levels. Nuclear reactions continue in the surrounding shells, and the release of neutrinos carries away immense amounts of energy, allowing further compression. The neutrino flux, although nearly invisible, plays a central role in the explosion mechanism, particularly in reviving the shock that forms after the core bounces. The protoneutron star emits neutrinos at a rate so high that it briefly outshines the rest of the star in energy output, transferring a fraction of this energy to the surrounding layers and helping drive the supernova explosion. Observational signatures of core collapse and its aftermath are influenced by these complex internal processes. Supernova light curves, the distribution of ejecta, and the formation of compact remnants all bear the imprint of rotation, magnetic fields, and the detailed composition of the core. Measurements of pulsar, spin rates, neutron star masses, and the properties of black holes provide indirect evidence of the extreme physics at play during collapse. Comparing these observations with theoretical models allows astrophysicists to refine their understanding of quantum pressures, exotic matter, and the thresholds that govern the fates of massive stars. Even subtle differences in core composition or angular momentum can lead to dramatically different outcomes. Two stars of similar initial mass may produce one neutron star and one black hole, depending on how silicon burning progressed, how neutrino emission cooled the core, and how magnetic fields redistributed energy and angular momentum. These variations illustrate the sensitivity of stellar death to internal conditions and highlight the richness of possible end states, from compact spinning neutron stars to invisible, gravitationally dominant black holes. The physics of core collapse is an extraordinary confluence of classical gravity and quantum mechanics. Electron degeneracy, neutron degeneracy, and exotic matter provide the pressures that resist gravity, while nuclear forces, neutrino emission, rotation, and magnetic fields influence the dynamics and symmetry of the event. The balance between these forces dictates whether a star produces a neutron star, a magnetar, or a black hole, and shapes the chemical and energetic legacy left behind. In this interplay of extremes, the death of a massive star becomes not only a cataclysmic finale, but also a laboratory for understanding matter under conditions that cannot be replicated on Earth. Ultimately, core collapse represents the culmination of millions of years of stellar evolution, the moment when quantum mechanics, nuclear physics, and gravity converge to produce some of the most extraordinary objects in the universe. It is a process of transformation where ordinary matter is compressed to densities beyond imagination, exotic states of matter emerge, and the ultimate fate of the star is determined. Through careful observation, theoretical modeling, and a growing understanding of fundamental physics, we are able to witness and interpret this dramatic finale, connecting the life and death of stars to the ongoing evolution of the cosmos. In the final moments of a massive star's life, an extraordinary flux of particles begins to emerge from the core, almost imperceptible yet carrying away immense energy. These are neutrinos, nearly massless and weakly interacting particles that escape almost unimpeded from the dense stellar interior. In the collapsing core, neutrinos become trapped temporarily, as densities climb to hundreds of trillions of grams per cubic centimeter, scattering repeatedly and influencing the flow of energy. This phenomenon, known as neutrino trapping, plays a crucial role in delaying collapse and transporting energy outward, maintaining the delicate balance between pressure and gravity for a few critical moments. Neutrinos are not uniform in type. They exist in flavors, electron, muon, and tau, and can oscillate between these flavors as they propagate, a behavior first confirmed through solar neutrino studies. These flavor oscillations affect how energy is carried away from the core and how neutrinos interact with the surrounding material. Research by Cecilia Lunardini, and George Fuller has shown that collective neutrino behavior can emerge in these extreme environments, where the density of neutrinos is so high that they interact with one another, creating complex self-regulating patterns of energy transport. These interactions can influence the symmetry of the collapsing core, contributing to slight deviations that later manifest in the asymmetry of the supernova explosion. Speculative sterile neutrinos, hypothesized particles that do not interact via the weak nuclear force, could further alter the dynamics of core collapse. While they have yet to be directly observed, their potential existence offers intriguing possibilities. Sterile neutrinos could carry energy away differently than standard neutrinos, modifying the distribution of pressure and altering the rate at which the core contracts. Such effects may produce subtle asymmetries in the collapse, influencing both the geometry of the explosion and the rotational properties of the resulting neutron star or black hole. Even small differences in energy transport can have macroscopic consequences, highlighting the delicate sensitivity of stellar death to fundamental particle physics. As the core collapses, neutrino-driven winds emerge from the surface of the proto-neutron star. These winds, powered by the intense flux of escaping neutrinos, accelerate material outward, ejecting it into the surrounding layers of the star. In doing so, they contribute to nucleosynthesis, the creation of new isotopes, particularly those that require rapid neutron capture. These processes help produce elements heavier than iron, including some of the rarest and most precious in the universe, and enrich the circumstellar environment with material that will later mix into the interstellar medium. Without neutrino-driven winds, the formation of these elements would be significantly less efficient, illustrating the subtle yet critical role of these ghostly particles. Detection of neutrinos from supernovae has provided remarkable insight into these hidden processes. The famous observation of neutrinos from supernova 1987A, captured by detectors such as Kamiokande and the Irvine, Michigan Brookhaven detector, confirmed that neutrinos carry away nearly 90% of the gravitational energy released in core collapse. These detections, consisting of only a few dozen events, allowed scientists to validate theoretical models of core collapse, confirming the immense energy and rapid timescales involved. Modern detectors, including Super Kamiokande, IceCube, and the Sudbury Neutrino Observatory, continue to refine our understanding, enabling precise measurements of neutrino flux, energy spectra, and flavor composition. The influence of neutrinos extends beyond energy transport. As they interact with surrounding material, they deposit momentum, driving subtle convection and assisting in the revival of the stalled shock wave formed immediately after core bounce. This energy deposition is essential for initiating the outward propagation of the shock, allowing the outer layers of the star to be expelled and triggering the supernova explosion. The detailed behavior of neutrinos in this phase is a central focus of computational simulations, which model how collective effects, flavor oscillations, and interactions with dense matter govern the final energy transfer. Neutrinos also leave an imprint on the composition of the ejected material. Regions exposed to neutrino fluxes experience changes in neutron-to-proton ratios, affecting which isotopes are synthesized and in what abundance. This directly impacts the distribution of R process elements, providing the universe with heavy elements such as gold, platinum, and uranium. Observations of metal-poor stars in the Milky Way, combined with modeling of supernova nucleosynthesis, reveal patterns that trace back to the intricate role of neutrinos during core collapse. Rotation and magnetic fields further complicate the influence of neutrinos. In a rapidly rotating or magnetized proto-neutron star, neutrino emission may be anisotropic, preferentially escaping along certain directions and contributing to asymmetrical energy deposition. This can enhance jet formation, drive non-spherical outflows, and affect the final angular momentum of the remnant. Such asymmetries are subtle yet critical, helping to explain why some supernova remnants display elongated or clumpy structures, and why neutron stars often possess significant spin and magnetic fields. Even the tiniest details in neutrino physics can have outsized consequences. The precise rates of neutrino interactions, the probabilities of flavor conversion, and the presence or absence of sterile neutrinos all feed into the dynamics of the collapse. The core responds sensitively to these inputs, adjusting its contraction rate, the distribution of energy, and the efficiency of shock revival. In this way, the invisible and nearly intangible neutrinos orchestrate a profound transformation, shaping the explosion, the remnant, and the elements that will seed future stars. Ultimately, neutrinos are the ghostly actors in the death of massive stars. They carry energy away, sculpt the core, drive nucleosynthesis, and influence the asymmetry and energetics of the supernova. Though nearly undetectable and fleeting in their interactions, their effects are both vast and enduring, linking the deepest microphysics within the collapsing core to the spectacular macroscopic phenomena that light up galaxies. By studying these particles, both directly through detectors and indirectly through supernova observations, we uncover the hidden choreography of forces that governs the final moments of some of the universe's most massive and influential stars. When the core of a massive star finally succumbs to gravity, the outer layers are left in a state of violent disequilibrium. A shock wave forms as the inner core rebounds against the incompressible nuclear matter. Yet this shock alone is insufficient to expel the star's envelope. Instead, the stalled shock must be revived by a delicate interplay of forces and instabilities, among the most important of which is the standing accretion shock instability, or as ASI. SASI arises when matter continues to fall onto the stalled shock, producing oscillations and sloshing motions that enhance turbulence, redistribute energy, and break the spherical symmetry of the collapsing core. These motions are far from trivial. They determine whether the shock can gain sufficient energy to drive a successful supernova explosion. Multidimensional simulations by H. Thomas Janka and Adam Burrows have shown that SASI is essential in massive stars above roughly 8 to 10 solar masses. Unlike earlier one-dimensional models, these simulations reveal the complex convective flows, lateral motions and anisotropies that can develop in the post-shock region. Convection is driven not only by neutrino heating, but also by the unstable flow patterns created by SASI, forming large-scale plumes that transfer energy outward. These plumes contribute to uneven expansion of the shock, producing asymmetrical ejection of material and imprinting directional features on the supernova remnant. Neutrino heating plays a central role in this process. As the protoneutron star emits a torrent of neutrinos, some are absorbed by the surrounding layers of the stalled shock. This deposition of energy increases pressure, driving matter outward and aiding shock revival. The combination of neutrino heating, SASI-induced turbulence, and convection creates a feedback loop. Rising plumes enhance energy transport, while descending flows carry cooler material back toward the core, maintaining a dynamic but self-regulating system. It is in this complex environment that the outward shock finally accelerates, transitioning from a stalled feature to a rapidly expanding front that will ultimately disrupt the star. Less widely known theorists, such as Todd Thompson, Westian D.T. Msen, have explored how magnetoneutrino effects can further influence the dynamics of shock revival. In rapidly rotating or magnetized cores, magnetic fields can channel neutrino energy preferentially along certain directions, altering the symmetry of the explosion. This interaction can amplify instabilities, produce jet-like structures, and contribute to the uneven distribution of ejecta. While these effects are subtle compared to the dominant SASI and convective processes, they demonstrate the layered complexity of supernova mechanics and the sensitivity of the explosion to both microphysical and macroscopic conditions. The geometry of the shock front is rarely spherical. Observations and simulations reveal that massive stars explode with a variety of shapes, bipolar, clumpy, or even jet-like. The initial asymmetries seeded by SASI and convection are amplified as the shock propagates outward, interacting with the complex density structure of the overlying shells. Dense clumps may lag behind, while less resistant regions accelerate, creating finger-like protrusions of ejected material. These asymmetries can have long-term consequences, influencing the morphology of the supernova remnant, the kick velocity of the resulting neutron star, and the distribution of heavy elements into the interstellar medium. Jet formation is an extreme manifestation of these dynamics. In rapidly rotating cores with strong magnetic fields, energy can be funneled along the rotational axis, producing narrow, high-velocity outflows. These jets carry a significant fraction of the explosion's energy, carving channels through the outer layers and contributing to highly directional ejection of matter. Even in cases where jets do not dominate, smaller-scale anisotropies guide the expansion of the shock and the dispersion of synthesized elements, linking internal dynamics to observable features such as light curve asymmetries and spectral line broadening. Shock revival is therefore a cooperative process. The stalled shock is not a passive structure. It interacts continuously within falling matter, convective currents, SASI-induced oscillations, neutrino heating and magnetic effects. Each mechanism contributes to restoring outward momentum, enabling the supernova to succeed. The timing of shock revival is critical. If the shock accelerates too slowly, infalling material can overwhelm it, leading to a failed explosion and direct collapse into a black hole. If it accelerates efficiently, the star is disrupted, dispersing its outer layers and leaving behind a compact remnant such as a neutron star or magnetar. The distribution of ejecta reflects the history of these instabilities. Heavy elements, formed in the inner shells, may be propelled along certain directions by the combined effects of SASI and convection, while lighter elements in the outer shells respond differently to shock propagation. This stratification is often visible in supernova remnants, where observations reveal clumps, filaments, and jets of material. The complex internal choreography ensures that even the most seemingly chaotic explosion follows patterns dictated by the underlying physics, a testament to the deterministic nature of these extreme environments. Simulations continue to reveal new subtleties. Three-dimensional modeling captures interactions that two-dimensional approaches cannot, showing how plumes, vortices, and instabilities evolve over milliseconds to seconds. They demonstrate that small variations in initial rotation, magnetic field strength, or core structure can significantly alter the explosion geometry, emphasizing the sensitivity of supernova outcomes to the star's internal state. These insights highlight why no two supernovae are identical, even among stars of similar mass and composition. Ultimately, the mechanics of supernova explosions are a narrative of instability harnessed. SASI, convection, neutrino heating, and magnetic effects collectively orchestrate the transformation of a collapsing core into a spectacular outward explosion. The asymmetries and directional flows are not random but arise from the interplay of forces within the star, setting the stage for the formation of compact remnants, the dispersal of heavy elements, and the ongoing evolution of galaxies. In observing supernova remnants and modeling their dynamics, we glimpse the hidden forces that govern these cosmic cataclysms, revealing the elegant complexity behind the violence of stellar death. The death of a massive star is not merely an endpoint, it is a profound act of creation, seeding the cosmos with elements forged over millions of years. Nucleosynthesis, the process by which stars build heavier elements from lighter ones, occurs through several key pathways, each responsible for particular classes of nuclei. The rapid neutron capture process, or R process, occurs in environments with extreme neutron densities, such as the neutron-rich ejecta of a core-collapse supernova. Nuclei rapidly absorb neutrons, building up isotopes far heavier than iron in mere seconds. This is the mechanism responsible for many of the universe's heaviest and rarest elements, including gold, platinum, and uranium, creating a cosmic treasury that will eventually be incorporated into planets and, perhaps, life itself. The slow neutron capture process, or S process, operates over much longer timescales, typically in the interiors of asymptotic giant branch stars and during helium shell burning in massive stars. Neutrons are captured gradually, allowing beta decay to stabilize the nuclei before another neutron is absorbed. This method produces stable isotopes of elements such as strontium, barium, and lead, contributing to the overall abundance patterns observed in the galaxy. The S process is a quiet, steady companion to the more violent R process, demonstrating that both explosive and gradual mechanisms combine to populate the periodic table throughout cosmic history. A third pathway, the proton capture or P process, is responsible for certain rare, proton-rich isotopes that cannot be produced via neutron capture. These isotopes, often lying on the P-rich side of the chart of nuclides, form during intense photodisintegration reactions when gamma photons strip neutrons from pre-existing nuclei, allowing subsequent proton captures to occur. The P process complements the R and S processes, filling in the rare gaps of isotopic abundances and highlighting the intricate balance of nuclear reactions required to generate the diversity of elements we observe. Researchers such as Kenichi Nomoto have provided extensive models of how these processes unfold in massive stars, mapping out the conditions under which each pathway dominates. Nomoto's work demonstrates that the relative contribution of R, S, and P processes depends not only on the mass and metallicity of the star, but also on the timing and dynamics of shell burning and core collapse. Francesca Mattiucci, has explored the broader implications of these nucleosynthesis pathways for galactic chemical evolution, showing how the cumulative effects of many generations of stars build the abundance patterns observed in the Milky Way and other galaxies. The materials synthesized in massive stars are expelled into the interstellar medium during supernova explosions, mixing with gas clouds and dust. These enriched regions provide the raw ingredients for the next generation of stars and planets, ensuring that each successive cycle of star formation begins with a slightly different chemical composition. The enrichment process is not uniform. Clumps of heavier elements may be dispersed preferentially along certain directions due to asymmetries in the explosion, forming pockets of enhanced metallicity that influence local star formation. Observations of young star clusters and molecular clouds reveal these variations, confirming that the chemical fingerprints of massive stars are preserved and passed on through cosmic time. Supernova remnants themselves serve as laboratories for studying nuclear synthesis. Detailed spectroscopy reveals emission lines corresponding to elements such as oxygen, silicon, calcium, and iron, providing a direct link between theoretical predictions and observable reality. High-resolution imaging shows the distribution of these elements within the remnant, often in clumpy or filamentary structures that reflect the turbulent dynamics of the explosion. These patterns not only validate models of nuclear synthesis, but also reveal the interplay between stellar physics and hydrodynamic processes during supernovae. The connection between nuclear physics and cosmic chemical evolution is profound. The rates of individual nuclear reactions, the availability of neutrons, and the energy released in each fusion or capture event determine the types and abundances of isotopes produced. Small variations in reaction cross-sections or neutron fluxes can propagate through the layers of the star, influencing the composition of the core and the resulting ejecta. Over millions of years and billions of stars, these microscopic differences accumulate, shaping the chemical diversity observed in galaxies and informing models of planet formation, planetary chemistry, and the potential for life. Energy transport during nucleosynthesis also plays a critical role. Fusion and capture reactions release vast quantities of energy, driving convection and circulation within the star. These flows not only redistribute elements, but also maintain pressure gradients, supporting the star against gravitational collapse. When the star reaches the end of its life, the composition and distribution of these synthesized elements influence the dynamics of the supernova shockwave, affecting how efficiently the outer layers are expelled and how isotopes are mixed into the surrounding medium. The fate of the elements is thus intimately tied to the mechanics of stellar death, linking microphysics to the evolution of galaxies. The diversity of isotopes produced is staggering. Light elements such as carbon and oxygen are synthesized over millions of years, forming the backbone of future planetary systems, while heavier nuclei such as iron, nickel, and zinc are forged in the final moments of the star's life. The R process adds rare neutron-rich isotopes, while the P process fills in the proton-rich species. Collectively, these processes ensure that each supernova contributes a rich and varied palette of elements, seeding the galaxy with the ingredients necessary for planets, chemistry, and life itself. Observations of metal-poor stars and ancient globular clusters provide further confirmation of nucleosynthesis pathways. The relative abundances of R process and S process elements in these stars reflect the cumulative contributions of many generations of massive stars, tracing the chemical evolution of the galaxy back billions of years. Supernova remnants such as Cassiopeia display intricate distributions of iron, oxygen, and silicon, demonstrating how elements synthesized deep in the core are carried outward and dispersed. These data link detailed nuclear physics to large-scale galactic processes, providing a bridge between the interior of a single star and the composition of entire stellar populations. Ultimately, nucleosynthesis and galactic recycling are processes that transform the death of a massive star into a legacy for the cosmos. The interplay of R, S, and P processes, moderated by fusion dynamics, neutrino flux, and convective mixing, determines which elements are created and how they are distributed. These newly forged materials enrich the interstellar medium, influence the formation of new stars, and seed the next generation of planets. Through careful observation and theoretical modeling, we can trace the journey of each nucleus from its birth in the heart of a star to its role in shaping the chemical landscape of the galaxy, revealing the profound connections between the physics of the very small and the evolution of the very large. When a massive star completes its final collapse, it can leave behind one of the most extraordinary objects in the universe, a neutron star. These remnants are incredibly dense, packing more mass than the Sun into a sphere only about 20 kilometers across. The interior of a neutron star is a complex layered structure, beginning with a thin outer crust composed of nuclei immersed in a sea of electrons. Beneath this lies the inner crust, where neutron-rich nuclei coexist with a superfluid of free neutrons, forming exotic nuclear pasta phases that resemble sheets, tubes, or spaghetti-like filaments. These structures influence thermal conductivity, mechanical strength, and the way the crust responds to stresses, playing a key role in phenomena such as starquakes and pulsar glitches. Deeper still, the core is a realm of extremes. Matter is compressed to densities exceeding nuclear saturation, and the behavior of such dense matter is described by the equation of state, which relates pressure, density, and temperature. Researchers such as Anna Watts, Ainiyam Dubwaitiyam, and Madhapa Prakash have studied these equations in detail, exploring how different compositions, from neutrons alone to mixtures including hyperons, meson condensates, or even deconfined quark matter, affect the star's mass, radius, and stability. These theoretical models allow astrophysicists to connect the internal physics of neutron stars to observable quantities, providing insight into fundamental nuclear interactions that cannot be recreated on Earth. Neutron stars are not merely static spheres. They spin, sometimes hundreds of times per second, producing pulsars whose beams sweep across space like cosmic lighthouses. The rotation interacts with the internal superfluid and solid crust, leading to sudden shifts in spin known as rotational glitches. These events provide a window into the coupling between the crust and the interior superfluid, revealing the mechanical and dynamic properties of matter at supranuclear densities. Magnetaires, a subset of neutron stars, possess magnetic fields trillions of times stronger than Earth's, exerting forces that deform the crust, drive starquakes, and produce high-energy radiation bursts that can be detected across the galaxy. Understanding these magnetic phenomena requires a synthesis of stellar evolution, quantum mechanics, and plasma physics. Color superconductivity is another exotic aspect of neutron star cores. At the extreme densities present, quarks may form paired states, analogous to electron pairing in terrestrial superconductors, producing a state in which the core exhibits superconducting and superfluid properties simultaneously. This has profound implications for thermal conductivity, magnetic field behavior, and rotational dynamics, influencing the long-term evolution of the star. While direct observation of color superconductivity remains beyond current technology, its effects may be inferred from cooling rates, rotational behavior, and magnetic field evolution. Gravitational waves have emerged as a powerful tool for probing these dense interiors. Asymmetric rotation, crustal deformations, and binary mergers involving neutron stars produce ripples in spacetime detectable by observatories such as LIGO and Virgo. The amplitude, frequency, and waveform of these gravitational waves encode information about the neutron star's mass, radius, equation of state, and internal composition. Observing these signals provides a unique avenue for testing theories of dense matter physics and connecting the behavior of neutron stars to the core properties of their progenitor massive stars. The composition and behavior of a neutron star's interior are intimately linked to the star from which it formed. The mass of the progenitor, the distribution of angular momentum, and the dynamics of the core collapse influence the resulting neutron star's rotation rate, magnetic field, and mass. Stars that experienced rapid rotation or strong magnetic fields during collapse often produce neutron stars with higher spins or more intense fields. Likewise, variations in nucleosynthesis and shell burning during the progenitor's life leave imprints in the neutron-rich crust, connecting observations of pulsars and magnetars to the internal processes that preceded their formation. Observational evidence provides crucial insights into these phenomena. Precision timing of pulsars reveals spin-down rates and sudden glitches, which can be analyzed to infer crustal properties and superfluid dynamics. X-ray and gamma-ray observations of magnetars reveal bursts, flares, and long-term decay of magnetic fields, offering a window into the interaction between magnetism and dense matter. Thermal emissions, spectral features, and timing variations together allow astronomers to reconstruct the internal conditions, connecting the observable behavior to theoretical models of neutron star interiors. Rotation continues to play a defining role long after the star is formed. Rapidly spinning neutron stars experience centrifugal forces that modify their shape, making them slightly ablate. In combination with strong magnetic fields, this can generate asymmetries that radiate gravitational waves continuously. These persistent signals provide ongoing constraints on the star's internal structure, offering a non-invasive method to probe densities and interactions otherwise inaccessible to direct observation. Observing these signals over time allows scientists to track the evolution of angular momentum and magnetic energy in these extraordinary objects. Neutron stars also serve as laboratories for the extremes of physics. Their density, pressure, and magnetic field strength reach levels impossible to replicate on Earth, offering a testing ground for theories of nuclear interactions, superfluidity, superconductivity, and general relativity. The interplay between crustal mechanics, superfluid interiors, and magnetic forces creates phenomena that are both rich and complex, from pulsar glitches to magnetar flares. Each observation provides feedback to refine equations of state and deepen our understanding of matter under conditions that push the limits of physical theory. Ultimately, neutron stars are the living echoes of massive star deaths, translating the violent physics of core collapse into enduring cosmic structures. Their interiors, shaped by density, magnetism, rotation, and exotic states of matter, retain a memory of the progenitor's mass, composition, and rotational history. By studying pulsars, magnetars, gravitational waves, and thermal emissions, astrophysicists can reconstruct the life stories of these remnants, connecting the microscopic physics of nuclear interactions to macroscopic astrophysical phenomena. In this way, neutron stars serve not only as objects of fascination, but as laboratories of dense matter, allowing us to explore the universe's most extreme conditions from a distance and uncover the hidden legacy of massive stellar evolution. When a massive star exceeds the limits that neutron degeneracy pressure can support, it collapses into a black hole, an object so dense that not even light can escape its gravitational grasp. Stellar mass black holes, typically ranging from a few to tens of times the mass of the Sun, are formed in the aftermath of core collapse supernovae or through direct collapse in the most massive stars. Surrounding these black holes, gas and debris often form an accretion disk, a swirling maelstrom of material heated to millions of degrees by friction and gravitational compression. As matter spirals inward, immense energy is released, and in some cases, relativistic jets are launched along the rotational axis, projecting high-energy particles across thousands of light-years and influencing the surrounding interstellar medium. Andrew King has explored how accretion feedback from stellar mass black holes can impact their galactic environment. The energy released by infalling matter not only heats surrounding gas, but can also regulate star formation in nearby regions, either suppressing it by dispersing molecular clouds or triggering it by compressing gas along jet paths. This feedback is critical in understanding how even small black holes contribute to the larger-scale dynamics of galaxies, linking phenomena on the scale of tens of kilometers to structures spanning hundreds of thousands of light-years. Black holes come in different varieties. The Kerr black hole describes a rotating solution to Einstein's equations of general relativity, characterized by mass and angular momentum. Its rotation drags space-time around it, a phenomenon known as frame dragging, which affects the dynamics of the accretion disk and the formation of relativistic jets. In contrast, the Reissner-Nordstrom black hole includes electric charge in addition to mass, leading to distinct horizons and space-time structures. While astrophysical black holes are expected to have negligible charge, studying these theoretical solutions provides insight into the range of possibilities permitted by general relativity and the fundamental behavior of space-time near singularities. Beyond stellar remnants, speculation exists about primordial black holes, hypothesized to have formed in the extreme density fluctuations of the early universe, moments after the Big Bang. If they exist, these primordial objects could account for a fraction of the elusive dark matter, influencing galactic dynamics and the evolution of large-scale structure. While no conclusive detections have been made, the idea remains a compelling intersection of cosmology, particle physics, and gravitational theory, illustrating the diversity of black hole formation pathways beyond conventional stellar collapse. Observational advances have transformed our understanding of black holes. The Event Horizon Telescope provided the first direct image of a black hole's shadow in the galaxy M87, confirming the predictions of general relativity and extreme gravitational fields. Meanwhile, gravitational wave observatories such as LIGO and Virgo have detected mergers of stellar mass black holes, revealing the masses, spins, and frequencies of these events with exquisite precision. These observations allow astrophysicists to probe properties previously considered unmeasurable, connecting theoretical predictions with empirical data and expanding our knowledge of compact object populations across the universe. Accretion physics is central to understanding black hole feedback. Material in the disk loses angular momentum through viscous processes, spiraling inward while heating and radiating energy. This energy release can rival the luminosity of entire galaxies, particularly when channeled into jets. Observations of X-ray binaries and ultraluminous X-ray sources provide direct evidence of this process, showing how black holes convert gravitational potential energy into radiation and kinetic energy, with implications for their surroundings and for galactic evolution. Relativistic jets, while spectacular, are also sensitive indicators of the black hole's spin and magnetic field configuration. Magnetic fields in the accretion disk can thread the event horizon, extracting rotational energy from the black hole through mechanisms such as the Blandford-Zniak process. These jets can travel at a significant fraction of the speed of light, sculpting the interstellar medium and creating shock fronts that accelerate cosmic rays. The orientation, collimation, and stability of these jets provide insight into the extreme physics occurring just outside the event horizon, bridging observational astronomy and relativistic magnetohydrodynamics. Black hole mergers observed through gravitational waves reveal additional layers of complexity. The waveform encodes information about the masses, spins, and orbital dynamics of the colliding black holes. Analysis of these signals allows researchers to infer the rate of black hole formation, the distribution of masses in stellar remnants, and even the presence of pre-merger asymmetries. Each detection adds to a growing catalogue, offering statistical insight into how stellar evolution, binary interactions, and collapse physics produce the population of black holes that populate our galaxy and beyond. The environment surrounding a black hole is a dynamic laboratory. Matter, spiraling into the accretion disk, experiences tidal forces strong enough to stretch and heat it, producing X-rays and gamma rays detectable across intergalactic distances. Magnetic fields mediate energy transfer, driving turbulence in the disk and channeling material into jets. Observations of these emissions combined with theoretical models provide constraints on the mass, spin, and inclination of the black hole, linking the dynamics of matter on scales of kilometers to phenomena observable across millions of light-years. In the most extreme cases, black holes act as engines of galactic evolution. The energy and momentum injected by accretion disks and jets influence star formation, regulate gas inflows, and drive chemical enrichment. Even stellar mass black holes, once thought too small to affect their environment, contribute cumulatively to these processes, as outlined in the work of Andrew King. This demonstrates that the life cycle of massive stars extends beyond their immediate collapse, with their remnants participating actively in shaping galaxies over millions of years. Ultimately, black holes embody the extremes of physics, regions where gravity dominates, space-time is warped to its limits, and energy is extracted with astonishing efficiency. From stellar mass remnants with accretion disks and jets to hypothetical primordial black holes potentially connected to dark matter, these objects link the death of stars to the ongoing evolution of galaxies. Observations from the Event Horizon Telescope LIGO and Virgo provide direct insight into these phenomena, allowing us to witness the interplay of mass, spin, and magnetic fields in environments that push the boundaries of what is physically possible. In studying black holes, we observe both the ultimate consequence of massive stellar collapse and the profound influence these singularities exert on the cosmos around them. The death of massive stars reverberates far beyond the boundaries of the star itself, influencing the structure, composition, and evolution of entire galaxies. When a supernova explodes, it injects enormous amounts of energy into the surrounding interstellar medium, creating shock waves that compress gas clouds, trigger turbulence, and sometimes ignite the formation of new stars. These shocks, traveling at thousands of kilometers per second, act as cosmic sculptors, carving cavities and shells into the surrounding gas while simultaneously distributing heavy elements synthesized during the star's life and death. The result is a cycle in which the death of one star seeds the birth of many others, establishing a dynamic feedback loop that drives the evolution of galaxies over millions of years. Black holes contribute to this process in complementary ways. Even stellar mass black holes, through accretion and jet formation, inject energy into their surroundings, influencing gas density, temperature, and angular momentum. On a larger scale, supermassive black holes at the centers of galaxies, often seen as active galactic nuclei or AGN, provide an analogous mechanism, releasing prodigious amounts of energy through accretion disks and relativistic jets. These feedback processes regulate star formation, suppressing it in some regions by heating or expelling gas, while simultaneously compressing gas elsewhere, encouraging new stellar nurseries. The parallels between stellar feedback and AGN activity illustrate how energetic processes at vastly different scales share common physical principles, linking small-scale stellar events to galactic evolution. Elena Rossi, has extensively studied the impact of stellar feedback on galaxy evolution, emphasizing how energy and momentum from massive star deaths influence both local and large-scale dynamics. The injection of turbulence from supernovae stirs the interstellar medium, preventing gas from collapsing too quickly and sustaining ongoing star formation over extended timescales. At the same time, the enrichment of the interstellar medium with heavy elements modifies the cooling properties of gas clouds, altering how quickly and efficiently stars form. This chemical feedback, combined with energy injection, ensures that galaxies maintain a balance between growth and regulation, preventing runaway star formation that would otherwise exhaust available gas prematurely. Shock-triggered star formation is one of the most visually striking consequences of supernova feedback. As a shock wave sweeps through a dense molecular cloud, it compresses regions of gas beyond critical density thresholds, initiating collapse and the formation of new protostars. This mechanism can produce clusters of stars along the edges of supernova remnants, creating patterns that trace the explosive history of the progenitor star. Observations of regions such as the Orion Nebula and the Carina Nebula reveal these processes in action, showing bright arcs and knots where compressed gas has ignited the next generation of stellar birth. The interplay between destruction and creation underscores the interconnected nature of stellar life cycles within a galactic ecosystem. Turbulence injected into the interstellar medium also plays a vital role in shaping galactic structure. Supernovae stir gas on scales ranging from parsecs to hundreds of parsecs, influencing the distribution of molecular clouds, regulating star formation efficiency, and contributing to the thickness and stability of galactic disks. This turbulent energy interacts with magnetic fields, cosmic rays, and gravitational instabilities, creating a complex, dynamic environment in which subsequent generations of stars form. Over time, the cumulative effect of countless stellar deaths governs the morphology, star formation rate, and chemical evolution of entire galaxies. Chemical enrichment is a central aspect of this feedback. Massive stars synthesize heavy elements such as carbon, oxygen, silicon, and iron, releasing them into space during supernova explosions. These elements provide the building blocks for planets, atmospheres, and ultimately life. The distribution of these elements within the galaxy is uneven, shaped by the dynamics of the explosion, the pre-existing structure of the interstellar medium, and the motion of stellar remnants. Observations of metal abundances in different regions of the Milky Way, combined with supernova remnant studies, allow astronomers to trace the flow of these elements, connecting individual stellar deaths to the broader chemical evolution of galaxies. Feedback from black holes complements this process by regulating the availability of gas for star formation. Accretion-powered outflows can expel material from dense regions, suppressing further stellar birth locally, while simultaneously injecting energy that maintains turbulence and prevents gravitational collapse on larger scales. This dual role ensures that galaxies evolve in a controlled manner, avoiding excessive star formation that would deplete gas reservoirs too rapidly. The combination of supernova-driven turbulence, chemical enrichment, and black hole feedback creates a self-regulating system in which star formation, chemical evolution, and galactic dynamics are tightly coupled. Individual stellar deaths are therefore directly linked to the architecture of galaxies. The mass, composition, and timing of supernovae influence the rate at which gas is recycled, the distribution of metals, and the density structure of the interstellar medium. Over millions of years, these effects accumulate, shaping spiral arms, star-forming regions, and even triggering the formation of new molecular clouds. By observing the remnants of supernovae, measuring chemical abundances in star clusters, and modeling the effects of black hole feedback, astrophysicists can connect the life cycle of a single star to the evolution of large-scale cosmic structures, revealing the profound influence that individual stellar deaths exert across galactic scales. The synergy between energetic feedback, chemical enrichment, and dynamic regulation ensures that galaxies remain vibrant ecosystems, capable of sustaining star formation over billions of years. Supernovae, neutron stars, and black holes collectively sculpt the interstellar medium, inject turbulence, and enrich gas with the heavy elements necessary for the next generation of stars. In this way, the death of massive stars becomes a driving force in galactic evolution, linking the violent end of a single star to the ongoing story of cosmic structure, chemical diversity, and the formation of planets and life. The echoes of each stellar death resonate far beyond its immediate surroundings, leaving an indelible imprint on the galaxy and ensuring that the universe continues to evolve in a complex, interconnected dance. As we reach the frontier of our understanding, massive stars present mysteries that stretch across the boundaries of physics, astronomy, and cosmology. The interiors of collapsing stars and the nature of their remnants push us to consider exotic particles and states of matter. Axions, hypothetical particles proposed to solve the strong charge parity problem in quantum chromodynamics, could influence energy transport in stellar cores and alter the cooling rates of neutron stars. Sterile neutrinos, another speculative class of particles, might subtly affect core collapse dynamics, introducing asymmetries or modifying the neutrino flux that drives supernova explosions. Even the quark-gluon plasma, a state of matter in which quarks and gluons are deconfined, may exist briefly in the densest cores of the most massive stars, providing a window into conditions otherwise found only in the earliest moments of the universe. Fundamental uncertainties remain in the thresholds that determine whether a collapsing core forms a neutron star or a black hole. Observationally, neutron stars are measured with masses up to roughly 2.3 times the mass of the Sun, yet theoretical models suggest that cores just slightly heavier may collapse directly into black holes. Factors such as rotation, magnetic fields, neutrino emission, and the stiffness of the equation of state all influence this transition, producing a region of ambiguity that remains a fertile ground for research. Understanding these limits is not merely academic. It shapes our knowledge of supernova rates, gravitational wave sources, and the population of compact objects throughout the galaxy. Exploring these questions requires an interdisciplinary approach. Nuclear physics provides insight into the behavior of matter at densities exceeding those in atomic nuclei, constraining equations of state and nuclear reaction rates. Relativity governs the extreme gravitational fields near neutron stars and black holes, dictating the dynamics of collapse and the propagation of shock waves. Cosmology connects these individual events to the evolution of galaxies and the distribution of elements across the universe. The interplay of these disciplines illustrates how the life and death of a single massive star can inform our understanding of the largest and smallest scales of the cosmos simultaneously. Reflective questions naturally arise when considering the broader impact of massive stars. How do the first generations of stars with virtually no metals shape the subsequent formation of galaxies and chemical evolution? To what extent does the variability of massive stars, from pre-supernova eruptions to rotation and magnetic activity, influence the distribution of heavy elements and the triggering of new star formation? Each answer we uncover raises new questions, revealing a universe in which every stellar death is both an ending and a beginning, influencing cosmic evolution in ways that ripple across space and time. The connection between microphysics and macroscopic structures is particularly striking. Subatomic interactions, nuclear reaction rates, weak interactions involving neutrinos, or hypothetical interactions with axions manifest in observable phenomena such as the luminosity of supernova, the kick velocities of neutron stars, or the chemical enrichment of interstellar gas. The microscopic behavior of particles informs the dynamics of collapsing cores, which in turn shapes the structure of galaxies, the formation of star clusters, and even the potential habitability of planets in distant systems. This continuous feedback between the very small and the very large underscores the elegant interconnectivity of the cosmos. While many of these ideas remain theoretical, ongoing observations and experiments continue to probe these frontiers. Gravitational wave detections of neutron star and black hole mergers offer new constraints on the maximum masses and equations of state of compact objects. High-energy neutrino observatories and X-ray telescopes provide glimpses into the processes occurring deep within collapsing stars. Laboratory experiments, including heavy ion collisions, recreate brief moments of extreme density and temperature, shedding light on the behavior of quark-gluon plasma and nuclear matter under conditions otherwise found only in stellar cores. Each line of evidence helps to refine our models, reduce uncertainties, and guide the next generation of inquiry. Ultimately, the study of massive stars at the edges of theoretical understanding invites both humility and wonder. We are confronted with phenomena that challenge our intuitions, test the limits of physics, and connect the infinitesimal to the infinite. By contemplating axions, sterile neutrinos, quark-gluon plasma, and the delicate thresholds between neutron stars and black holes, we confront the universe's complexity head-on, while recognizing that every discovery opens new horizons. The lives and deaths of massive stars are not merely isolated events. They are keystones in the architecture of the cosmos, linking nuclear physics, relativity, and cosmology in a grand and ongoing narrative that invites exploration, curiosity, and reflection.